So now that we know how to determine if a correlation exists between pairs of data values between two variables, the next question we want to ask is, well, if there is this linear relationship, what's the equation look like? What's the equation, the linear equation, that best fits this data? So you can see, I've got an example here. We've got some data that does appear to have a linear relationship. Those points are all pretty close to a line. So I'm kind of seeing this line cutting up through the middle here. And the question we're asking is, what's the equation? Right? What is the equation of the best fitting line? Right, well, the first thing we have to do to make this happen is define what we mean by best. Right, we have to put some kind of measurement to this. And the way we do this is we look at what are called the residuals. You can think of the residual as being the error. Right? So for example, if we take a look at this point right here, right, the actual data value is 63, maybe somewhere in that range, but my line is saying it's a little higher. My line is putting it at about, I don't know, 67, give or take. So the difference between the value I'm getting from my approximating line, my best fit line, and the actual data value, the technical term for this is called a residual. I usually just think of it as the error, right? It's how much your lie, it's how much your approximation differs from reality. So the way this best fit line is defined is it's the line that minimizes the squares of the residuals for every pair of points. All right, well, I'm not going to actually try to calculate the formulas here. When you see the formulas on the next slide, you'll probably realize why. They're not pleasant, right? And again, they're using the same concepts we've seen before. In the last section, we talked about the correlation coefficient, and earlier when we talked about things like standard deviation. We're taking these pairs of data values and we're doing things with them. We're adding up the x's, we're adding up the squares of the x's, we're adding up the products of the x's and the y's, and then you're doing this very messy calculation with them. And if you watch the correlation lecture, my feelings about these formulas are the same as they were for the formula for the correlation coefficient. I would never give a student a data set and say, hey, calculate these values. Right? The slope, by the way, the slope in the y-intercept is what we're calculating here. This is the slope of the best fit line, and this is the y-intercept of the best fit line. Calculating these by hand, even for a smallish data set, is just horrid. If I absolutely had to, I would put these numbers into Excel and let Excel do the x times y and the x squareds and adding them all up, and then I would just try to get them into the formula. Even that is unnecessarily complicated. Excel has formulas, built-in formulas, that will calculate these for you. The formula for the slope is slope, and the formula for the y-intercept is intercept. Now, the one thing you need to be careful of, and this absolutely drives me nuts every time I have to use these formulas, for some reason, the inputs are backwards. You have to give it the range of y values first and the x values second, and it's the same over here. The x's, see, I really want the x's to go first. The y's go in the first parameter, and the x's go in the second. Excel will gladly do this for you. Once you've got the data into Excel, it takes literally 3 seconds, right? And of course, there are other options. There are calculators that will do this. There are software packages that will do this. There really is just simply no cause to be doing this kind of thing by hand. What really is important to me as a professor, as a mathematician, is the students be able to do things with these values, to use them and interpret them. So that's really what we're going to focus on here. So I've got the equation up here at the top. You notice on the right-hand side, this is, mx plus b. It's a classic linear equation from all the way back, first semester, first year algebra back in high school. And notice my notation here on the left, though. I did not put y over here. X represents an actual value from the data or from the population. The number that we're getting from this equation is just the best approximation of that value. It is not itself a data value. It is not itself a population value. It's an approximation. That's why we've seen this before. We're talking about proportions, right? That's why we use this y hat symbol here to make it clear what we're talking about, right? That this is an approximate value coming from our calculations, not an actual value coming from the population. Okay, so now that we've got this, right, let's see what we can do with it. Well, I've got obviously a very simple data set here. If you really wanted to, you could calculate these MMB values by hand because the data set is fairly small. I did them in Excel. Right, Excel told me that the slope is 2.455 and the y-intercept is negative 2.73. So what I want to know is, based on these results, right, what is my approximate value for y when x is equal to 12? Well, we got this linear equation. We were given an x value. We were asked to find a y value. Use the equation. I'm going to put 12 in here for x, and you get your calculator out. That is 26.73. I'm gonna put this in here, and I know I'm putting this on the y row. Keep in mind, it's kind of why I changed colors. Keep in mind that is actually y hat. That's an approximate value based off of our best fit equation. Okay, so what you're seeing here is kind of an interesting thing. This idea of correlation and regression, it kind of breaks our mold a little bit. If you remember way back at the very beginning, I talked about statistics as having two main branches. It's got descriptive statistics and inferential statistics. Well, now we're kind of doing both worlds here, right? My linear regression line was descriptive statistics. I took this data and I did calculations and I messed with it and I combined it and I synthesized it down to this formula that describes in a best fit way my entire data set. So that's descriptive statistics, right? But look at what I just used it for. I just used it to infer something about the population. I just used it to infer what the population is going to be like for a data value that I didn't already know. So this is kind of it's hard to fit this into statistics classes sometimes. Where do you put it? Do you put it in between the two when you're talking about them? I like to put it here at the end because, again, if you watch the correlation lecture, you can be more precise about correlation if you know what hypothesis tests are, because you can use a hypothesis test to really pin down whether or not this linear relationship exists, right? So that's why I usually put it here at the end. All right, so let's talk a little bit about sensitivity. These two data sets here are fundamentally the same. You can kind of see that if you look closely at them. The only difference is this point here. For the second data set, I took that point and I kicked it down to here. I turned that one point into a significant outlier. Right? And I want you to see what effect that had. If you look at the R values, changing that one value made a huge change in the R values. I'm doing this just off the top of my head here. That's about a 30% change, right? About a 30% difference. And you can see there were similar kind of dramatic changes down here between the slopes and the y-intercepts. So we've seen this behavior before. Or we saw this behavior before when we were talking about the mean. Right? The mean is very sensitive to outliers, and we're seeing exactly the same thing here. So what does this mean in practical terms? Well, as you're looking at your data, you usually when you're doing this kind of analysis, the first thing you're going to do is graph it, because a picture really is worth 1,000 words with this particular topic. I'm going to look at that when I look at this data visually. This point here in my second data set, that point stands out like a sore thumb. Right? I'm going to look at that point and say, okay, wait a minute. Did somebody bump the machine? You know, what's going on? Why did I get that enormous outlier? And you have to seriously consider whether or not that was some kind of accident. And it would be justified to discard this value and just go with the ones that clearly are tightly correlated. There's risk there. You need to be really sure you know what's going on. Right? It could be that value isn't an outlier. It could be that value is a sign of something really interesting that only happens rarely, right? And it's worth not throwing away, but investigating more deeply, right? So that's a risky thing to do, and you need to be super careful before you make that kind of decision. All right, so what I've done here is, and I'm working with that same data value, that same data set. Excuse me, that same linear regression line. What I've done here is I've taken every pair of values. Well, not every pair. This is just a subset of them. But I've taken a bunch of the x values and a bunch of the y values. And what I did is I took the x values and I put them into my formula. I said, okay, what's the approximate value that I'm getting from my formula for these x values? Because remember what I said back at the beginning. How did we get this formula? This formula is based on the idea of minimizing the square of the residuals. Well, that's what I've done here. So I've calculated the residuals. I took y hat, my approximate value, and I subtracted. Make sure I get this. I always mix up the order of these things. That's the other way around. I took the actual value from the data, and I subtracted my approximate value, right? And the result that I get from doing that is the residual. And once again, you can think of that as the error, right? It's how far off my approximation is from the actual real world data value. And you'll notice, I just want to point this out here, some x values have more than one y value in my data, right? You can see right up here at the beginning. I have 3 1s and 3 different y values for each one, and that's going to happen, right? This is why we have to do this approximation business, right? There's going to be minor variations based on your instruments, based on just kind of natural variation out in the world. If you're trying to look, for example, for a correlation between age and cholesterol level, well, you may have 10 people in your sample with the same age, but they're all going to have different cholesterol values. Now, for this correlation to exist, you're hoping that they're all going to be very, very similar, very close cholesterol values, but they will almost certainly be different, and that's okay. Right? That's going to happen. So what I've done here is I've made this table, and I have calculated all of the residual values for the first, I don't know how many dozen or so points here, just so you kind of see how what the process looks like. Right? The residual is, think of it as the error. It's the actual value, the observed value, minus the approximation that we get from our formula. Now, what can we do with this? I didn't just do this just as an exercise. If we do a plot of those residuals, right? So what I've got here is I've got the x values here. Those are the independent variables. And what I've done up here is I've graphed the residuals. And I did that for our data here, and I did it for another data set that I put together on the other side, so that we can kind of compare them. What you want to see is a graph like the one on the left. You want to see something that appears random, right? And yes, there are tests we can do for randomness. That's for a later class. But so right now we're just kind of taking a visual approach. Those data are scattered all over the graph, all over the graph space. That's what I'm looking for. If you get something like what I have on the other side here, this data does not appear to be as random. I've got clumps. I've got a clump of values down here. I've got another kind of clump of values over here. If you're seeing something like this, you need to be suspicious. There might actually be a relationship here other than a linear one, right? And in fact, this data over here that I generated this data using y equals x squared as kind of the generating function, and then I added a little bit of randomness so the data weren't perfect. If you try to do a correlation coefficient for this, because the x values are all in a very tight range, it does come across looking linear. Because if you take a quadratic graph and you look at just a little tiny narrow piece of it, especially as the x values get bigger, it starts to look an awful lot like a straight line. It isn't, but visually it can appear to be, and it can appear to be to the point where it can actually fool our formula. Right? It can kind of trick our correlation formulas, correlation coefficient formula, into thinking there's a linear relationship when there really isn't. Right? So kind of looking at this residual is a backup method for saying, well, yes, there's a correlation, but is it really a linear correlation, or is there maybe something else going on here? Okay, so that brings us to the end of our discussion of correlation and regression, which is also the end of our discussion of hypothesis testing, and it is also the end of our discussion for this first semester class, right? For this introductory class in statistics.